Today, August 26th, 2026, NASA just published something about Voyager 2 that almost nobody is talking about yet. If you care about what is happening at the very edge of human reach in space, subscribe right now, because what just happened with this spacecraft changes what we know about interstellar space. Let me give you the full picture. Voyager 2 is over 13 billion miles from Earth right now. Think about that number for a moment. 13 billion miles. At the speed of light, a radio signal from NASA's Deep Space Network takes over 19 hours just to reach it. Then another 19 hours to receive any reply. So when engineers send a command to this spacecraft, they wait nearly 2 full days to find out if it worked. And on August 4th, 2026, they found out that it worked. NASA's Jet Propulsion Laboratory just confirmed the success of what the engineering team nicknamed the Big Bang, a risky, simultaneous, all-or-nothing power management overhaul performed on Voyager 2 that was months in planning and had zero room for error because if it had failed, Voyager 2 would have lost another science instrument before the end of this year. Instead, the Big Bang succeeded. Voyager 2 now has enough power to keep 3 science instruments running in interstellar space for at least another year beyond what was previously possible. And those 3 instruments are sitting over 13 billion miles away in an environment that no human-made object had ever entered before. Voyager 1 crossed the boundary in 2012, measuring things about interstellar space that cannot be measured any other way from anywhere else. That is what happened today. And to understand why it matters as much as it does, you have to understand what Voyager 2 actually is, where it actually is, and what it has been finding in the space between the stars that nobody knew existed before it got there. Voyager 2 was launched on August 20th, 1977, 17 days before its twin, Voyager 1, which launched on September 5th of the same year. The reason Voyager 2 launched first, even though it carries the number 2, is that it was sent on a slower, longer trajectory designed to take advantage of a rare planetary alignment that allowed it to fly past Jupiter, Saturn, Uranus, and Neptune in a single mission. That alignment only happens once every 176 years. NASA called the path the Grand Tour. Voyager 1 was sent on a faster route that only included Jupiter and Saturn, but would allow it to reach interstellar space sooner. Both probes were originally designed for a 5-year mission. Neither of them has stopped working. Voyager 2 is now nearly 49 years into a mission that was supposed to last 5. It visited Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. It remains to this day the only spacecraft in history to have flown past the ice giants Uranus and Neptune. Everything we know about those planets from direct in-person observation comes from a spacecraft that was built in the early 1970s, launched before personal computers existed, and is still operating today on a fraction of the power it started with. Power is the core issue that has been defining the Voyager mission for the last several years. Both probes use radioisotope, thermoelectric generators, devices that convert the heat produced by the radioactive decay of plutonium-238 into electricity. They are essentially nuclear batteries. Back when Voyager 2 launched in 1977, those generators were producing around 470 watts. Every year since, as the plutonium has continued to decay, output has dropped by about 4 watts per year. After nearly half a century, the power available to Voyager 2 is now so limited that every single watt has to be accounted for. The engineering team has been working through a carefully prioritized shutdown sequence for years, turning off heaters first, then backup systems, then science instruments one at a time, each in an order agreed upon by the science and engineering teams based on which instruments were still returning useful data from interstellar space versus which had effectively completed their scientific purpose. After the planetary flybys ended in 1989, Voyager 2 originally carried 10 science instruments. By the beginning of 2026, through a series of planned deactivations over many years, it was down to 3 active instruments: the magnetometer, the Plasma Wave Subsystem, and the Cosmic Ray Subsystem. Without the Big Bang intervention that JPL just confirmed successful, the Cosmic Ray Subsystem was scheduled to be shut off before the end of 2026, dropping Voyager 2 to just 2 instruments. The Big Bang has bought at least another year for all 3. What exactly is the Big Bang? JPL engineers describe it as a simultaneous swap of powered devices. The spacecraft had been using 3 heater devices to keep its thruster fuel lines from freezing, because if those lines freeze, the thruster stops working. The antenna cannot be pointed at Earth, and the mission ends permanently. The Big Bang turned those 3 heaters off and turned on 3 alternative devices that accomplish the same thermal management goal, but consume almost 10 watts less power in total. 10 watts sounds like nothing. In the context of a spacecraft with razor-thin power margins that loses 4 watts per year, 10 watts is an enormous gain. It is enough to postpone a science instrument shutdown by at least a year. The reason this was risky is the precision required. The swap had to be executed simultaneously, not sequentially. If the alternative thermal management devices did not come online fast enough after the heaters were cut, the fuel lines could begin to cool toward dangerous temperatures before protection was restored. The engineers tested the procedure on Voyager 2 during May and June 2026 because Voyager 2 is closer to Earth than Voyager 1, which means the 2-day command and response cycle is slightly shorter, and because Voyager 2 had a small amount more power to work with than its twin, making it the safer test subject. The test succeeded, the full implementation succeeded. NASA published the confirmation on August 4th, 2026. The plan is now to implement the same Big Bang procedure on Voyager 1, which is currently over 15 billion miles away and takes over 23 hours just to receive a signal in the coming months. Now, here's the part that answers the question of why any of this matters scientifically. Because Voyager 2 is not just floating through empty space out there. It is doing something no other instrument humanity has built can do. It is taking direct measurements inside the very local interstellar medium, the region of space that exists beyond the heliosphere. And the heliosphere is something you need to understand properly because it is one of the most important structures in the solar system and one of the least visible. The heliosphere is the enormous bubble of particles and magnetic fields generated by the sun. The solar wind, the constant stream of charged particles flowing outward from the sun in all directions, inflates this bubble and pushes it outward until the pressure of the solar wind balances the pressure of the interstellar medium surrounding it. The outer boundary of this bubble is called the heliopause. Inside the heliopause is solar territory. Everything inside it, all 8 planets, the asteroid belt, the Kuiper belt, all of it sits within the sun's bubble. Outside the heliopause is interstellar space. And the heliosphere does something critically important for life on Earth. It partially shields the solar system from galactic cosmic rays, the extremely high-energy particles that constantly stream through the galaxy from exploding stars, colliding neutron stars, and other violent events elsewhere in the Milky Way. Without the heliosphere acting as a partial shield, the level of cosmic ray radiation reaching the inner solar system would be significantly higher. The planets inside the heliosphere are living inside a protective structure that the sun itself creates and maintains. Understanding how that structure works, how thick it is, how variable it is, and how it interacts with the interstellar medium pressing against it from outside is fundamental to understanding how habitable this solar system actually is over astronomical timescales. Voyager 1 crossed the heliopause on August 25th, 2012 at a distance of about 121 astronomical units from the Sun, where 1 astronomical unit is the distance from Earth to the Sun, roughly 93 million miles. Voyager 2 crossed the heliopause on November 5th, 2018 at about 119 astronomical units, taking a slightly different path through the heliosphere that crossed the boundary in a different direction. When Voyager 2 crossed, something remarkable happened that could not be observed when Voyager 1 made the same crossing. Voyager 1's plasma science instrument had stopped working back in 1980. Voyager 2's plasma science instrument was still operational. So, for the first time, humanity had a working plasma instrument that could directly measure the plasma environment at the moment of the heliopause crossing, and then continue measuring it in interstellar space on the other side. The data that came back was full of surprises. When Voyager 2 crossed the heliopause, it recorded the plasma just outside the boundary as being approximately 30,000 to 50,000 Kelvin in temperature. That is between 30,000 and 50,000 degrees. Scientists had not predicted temperatures anywhere near that high in the local interstellar medium at that location. The interstellar medium was supposed to be cold, sparse, quiet. What Voyager 2 measured was plasma that was unexpectedly dramatically hotter than the models had predicted. The heliosphere, the region just inside the heliopause, where the solar wind slows before reaching the boundary, was also found to have a different structure than the models expected. The termination shock, the region where the solar wind first slows from supersonic to subsonic speeds before eventually hitting the heliopause, was different in shape and location than the models had predicted. The heliopause itself was found to be not a uniform, clean boundary, but a complex layered transition zone where properties shift across multiple distinct regions rather than changing sharply at a single line. What Voyager 2 has been detecting since entering interstellar space, and what its 3 remaining instruments are still measuring right now in August 2026, is the actual composition, density, temperature, and magnetic field structure of the space between our solar system and the nearest other stars. The magnetometer measures the magnetic field of the interstellar medium, which is not zero. There is a magnetic field in interstellar space carried there by plasma ejected by dying stars across billions of years of galactic history. The Plasma Wave Subsystem detects oscillations in the interstellar plasma, which allows scientists to measure the density of electrons in the medium surrounding the spacecraft. This is the same instrument that on Voyager 1 has been detecting persistent narrowband plasma wave emissions continuously since 2017, allowing scientists to map the density of the interstellar medium over stretches of space as the probe moves through it. The Cosmic Ray Subsystem, the third instrument still running on Voyager 2 thanks to the Big Bang success, measures the galactic cosmic rays streaming in from deep space. These measurements from outside the heliosphere tell scientists how much the heliosphere is actually shielding the solar system from these particles and how that shielding changes based on the solar cycle. The Sun goes through approximately 11-year cycles of activity. Near solar maximum, when the Sun is most active and producing the strongest solar wind, the heliosphere inflates slightly and provides slightly more shielding. Near solar minimum, it deflates slightly. Voyager's instruments in interstellar space can measure directly how the cosmic ray flux outside the heliopause varies over time, giving scientists the first direct outside-in view of the heliosphere's shielding effectiveness as it changes with solar activity. The data is also telling a story about the shape of the heliosphere itself, which has been debated for years. Before Voyager 2 crossed the heliopause, the standard model assumed the heliosphere had an elongated comet-like shape with a long tail streaming behind it in the direction opposite to the Sun's motion through the galaxy. Voyager 1 crossed the heliopause going roughly north out of the ecliptic plane. Voyager 2 crossed it going roughly south. The fact that both crossings happened at roughly similar distances from the Sun, about 119 to 122 astronomical units, despite being in completely different directions, suggests the heliosphere may be more spherical than the older models predicted. But the two crossings also show different magnetic field behaviors. Voyager 1 observed dramatic magnetic field fluctuations right at the heliopause. Voyager 2 did not see the same fluctuations at all. The heliopause looked structurally different in the two different directions the two spacecraft were traveling, which means the heliosphere is not symmetric. Its shape and its boundary properties vary depending on which direction you are looking. And we only have 2 data points of direct in situ measurement to work from. Every additional day that Voyager 2 continues operating and transmitting is another data point added to humanity's only direct measurement record of what the space outside our solar system actually looks like. The signals coming back from Voyager 2 arrive at the Deep Space Network antennas on Earth at extremely low power. The spacecraft's radio transmitter produces 23 watts of power, roughly the same as a refrigerator light bulb. By the time that signal travels over 13 billion miles and reaches Earth, it is spread across an enormous area of sky. The receiving dishes at the Deep Space Network facilities in California, Spain, and Australia have to combine their signals to detect the data stream, which arrives at 160 bits per second, a data rate comparable to the dial-up internet connections of the 1990s. At that rate, transmitting a single standard modern photograph would take hours. Everything Voyager 2 knows about interstellar space comes through that trickle, and engineers at JPL, some of whom have worked on this mission for decades and some of whom were not alive when it launched, manage this trickle with extraordinary care, prioritizing which data to downlink, when to downlink it, and how to keep the hardware alive long enough to downlink the next batch. The goal now following the Big Bang success is to keep Voyager 2's 3 instruments running through at least 2027 and potentially significantly longer if the hardware cooperates. The engineering team has stated that if both Voyagers remain healthy, the mission could potentially continue with at least one science instrument into the 2030s. Voyager 1 will also receive the Big Bang treatment in the coming months. On November 18th, 2026, Voyager 1 is projected to reach exactly 1 light day from Earth, the first human-made object to ever reach that symbolic distance. A message sent from Earth at that moment will take 24 hours to arrive at the spacecraft, another 24 hours for any response to return to Earth. 2 full days for a round-trip communication with something that human hands built and human minds continue to operate. Meanwhile, Voyager 2 will not reach 1 light day until November 2035. And the most realistic engineering estimates suggest it may not still be operating by that date, though the probe keeps surprising the teams working on it. What is at stake in keeping these instruments running is not just data for data's sake. It is the only current direct measurement of the very local interstellar medium that exists. Every other measurement of interstellar space is indirect, made by telescopes looking at absorption patterns in starlight or by instruments like the Interstellar Boundary Explorer that sense energetic neutral atoms streaming back into the solar system from the heliopause. Voyager 2 is physically inside interstellar space, physically in the medium, physically surrounded by it, measuring it from within. There is no substitute for that. There is no other instrument currently capable of that measurement. The next dedicated interstellar mission, if one is ever funded and launched, would take decades to reach the distances Voyager 2 is at today. So, the data coming back through that 19-hour signal path right now is genuinely irreplaceable. Every watt that the Big Bang saved is not just a watt of electricity. It is a measurement that could not be made any other way by any other means for potentially a generation. A spacecraft that launched 49 years ago, built with technology from the early 1970s, traveling at about 34,000 miles per hour through the space between the stars, still measuring, still transmitting, still teaching us things about the universe that we could not learn any other way. And on August 4th, 2026, a team of engineers sent a command that traveled 13 billion miles at the speed of light and came back with the news that it worked. The Big Bang succeeded. Voyager 2 keeps going. The signals from outside our solar system keep coming, and the universe beyond the heliosphere keeps turning out to be stranger and more interesting than the models predicted. That is where Voyager 2 is right now. That is what it is doing. And thanks to what happened today, it is going to keep doing it for at least another year. But the story does not end with power management and signal delays. It extends into the very nature of the space these probes are traversing. The interstellar medium is not the empty void that science fiction often portrays. It is a dynamic, complex environment filled with plasma, magnetic fields, and cosmic rays that interact in ways we are only beginning to understand. Voyager 2's measurements are providing the first direct evidence of these interactions, revealing a universe that is far more active and structured than we ever imagined. The implications of these findings are profound. They challenge our understanding of the solar system's boundary and its interaction with the galaxy. They suggest that the heliosphere is not a static shield, but a dynamic structure that responds to changes in both the solar wind and the interstellar medium. This has implications for our understanding of space weather, cosmic ray propagation, and even the potential for life on other worlds. If the heliosphere is more complex than we thought, then the environments of other star systems might be equally complex. And if the interstellar medium is hotter and more turbulent than expected, then the journey of future interstellar probes might be more challenging than we anticipated. Voyager 2 is not just a relic of the past. It is a pioneer of the future, paving the way for the next generation of explorers who will venture even farther into the unknown. As we look to the future, the legacy of Voyager 2 will continue to inspire. Its discoveries have opened up new avenues of research and new questions to explore. They have shown us that even after nearly 50 years, a spacecraft built with 1970s technology can still make groundbreaking discoveries. They have reminded us that the universe is full of surprises and that there is always more to learn. And they have demonstrated the power of human ingenuity and perseverance. The engineers and scientists who have kept Voyager 2 operating for nearly half a century have shown that with creativity and determination, we can overcome even the most daunting challenges. Their work has ensured that Voyager 2 will continue to be a source of discovery for years to come. The journey of Voyager 2 is far from over. Even as its power dwindles and its instruments are gradually shut down, it will continue to travel through interstellar space for billions of years. It will carry with it a message from Earth, a golden record containing sounds and images that represent the diversity of life and culture on our planet. This record is a testament to our curiosity and our desire to connect with the cosmos. It is a message in a bottle, cast into the cosmic ocean, hoping that one day it might be found by another civilization. Whether that happens or not, the record serves as a reminder of our place in the universe and our aspiration to reach beyond our home. The story of Voyager 2 is also a story of collaboration. It is a story of thousands of engineers, scientists, and support staff who have worked together over the decades to keep the mission alive. It is a story of international cooperation, with the Deep Space Network antennas in California, Spain, and Australia working in unison to maintain contact with the distant probe. It is a story of generations, with some of the original team members passing the torch to younger colleagues who were not even born when the spacecraft launched. This continuity of effort and dedication is what has made the Voyager mission possible. It is a reminder that great achievements are not the work of individuals, but of communities working together toward a common goal. As Voyager 2 continues its journey, it will eventually pass out of the local interstellar medium and into the broader galaxy. It will travel through regions of space that we can only imagine, encountering phenomena that we have yet to discover. It will be a silent witness to the evolution of the galaxy, a traveler through time and space. And though it will eventually fall silent, its legacy will endure. The data it has collected, the discoveries it has made, and the inspiration it has provided will continue to shape our understanding of the universe for generations to come. The success of the Big Bang procedure is a testament to the ingenuity of the Voyager team. It shows that even with limited resources, we can find ways to extend the life of our missions and continue to make discoveries. It is a reminder that innovation is not just about building new things, but also about finding new ways to use what we already have. The lessons learned from the Big Bang will inform future missions, helping us to design spacecraft that are more efficient and more resilient. They will also inspire us to think creatively about how we can overcome the challenges of exploring the far reaches of our solar system and beyond. In the end, the story of Voyager 2 is a story of hope. It is a story of our desire to explore, to understand, and to connect with the cosmos. It is a story of our ability to overcome obstacles and to achieve the seemingly impossible. And it is a story that will continue to inspire us for generations to come. As Voyager 2 travels through the stars, it carries with it the dreams and aspirations of humanity. It is a symbol of our curiosity and our courage, a reminder that we are not alone in the universe and that there is always more to discover. So, as we celebrate the success of the Big Bang and look forward to the future of the Voyager mission, let us remember the lessons it has taught us. Let us remember the power of collaboration, the importance of innovation, and the value of perseverance. And let us continue to reach for the stars, knowing that even the smallest spacecraft can make the biggest discoveries. The journey of Voyager 2 is a reminder that the universe is full of wonders and that our quest for knowledge is never truly over. It is a journey that will continue to inspire us for generations to come. The scientific community is already buzzing with excitement about the potential discoveries that Voyager 2 might make in the coming years. With the Big Bang success, the probe has been given a new lease on life, and its instruments are poised to capture data that could reshape our understanding of the interstellar medium. Scientists are particularly eager to see how the Plasma Wave Subsystem and the Cosmic Ray Subsystem will respond to changes in the solar cycle as we approach the next solar maximum. These measurements could provide crucial insights into the dynamics of the heliosphere and its interaction with the interstellar medium. But the implications of Voyager 2's mission extend far beyond the realm of science. It is a testament to the power of human curiosity and our desire to explore the unknown. In a world that is often divided by differences, the Voyager mission stands as a symbol of what we can achieve when we work together toward a common goal. It is a reminder that we are all citizens of the same planet, looking up at the same stars and wondering about the same mysteries. The golden record that Voyager 2 carries is a message of peace and unity, a reminder that despite our differences, we are all part of the same human family. As Voyager 2 continues its journey, it will also serve as a beacon of hope for future generations. It is a reminder that even in the face of seemingly insurmountable challenges, we can find ways to persevere and to achieve our goals. The success of the Big Bang procedure is a testament to the ingenuity and determination of the Voyager team, and it is a source of inspiration for all of us. It shows that with creativity and hard work, we can overcome even the most daunting obstacles. The legacy of Voyager 2 will also extend into the realm of education. The mission has already inspired countless students to pursue careers in science, technology, engineering, and mathematics. And as the probe continues to make discoveries, it will continue to inspire future generations of explorers. The data that Voyager 2 collects will be used in classrooms around the world, helping to teach students about the wonders of the universe and the importance of scientific inquiry. It will be a reminder that the pursuit of knowledge is a noble and worthwhile endeavor, and that there is always more to learn. In the end, the story of Voyager 2 is a story of the human spirit. It is a story of our desire to explore, to understand, and to connect with the cosmos. It is a story of our ability to overcome obstacles and to achieve the seemingly impossible. And it is a story that will continue to inspire us for generations to come. As Voyager 2 travels through the stars, it carries with it the dreams and aspirations of humanity. It is a symbol of our curiosity and our courage, a reminder that we are not alone in the universe and that there is always more to discover. So, as we look to the future, let us remember the lessons of Voyager 2. Let us remember the power of collaboration, the importance of innovation, and the value of perseverance. And let us continue to reach for the stars, knowing that even the smallest spacecraft can make the biggest discoveries. The journey of Voyager 2 is a reminder that the universe is full of wonders and that our quest for knowledge is never truly over. It is a journey that will continue to inspire us for generations to come. The Voyager mission has also sparked a renewed interest in interstellar exploration. Space agencies around the world are now considering new missions that could build on the legacy of Voyager 2. Concepts for interstellar probes that could travel faster and farther than ever before are being discussed, and new technologies are being developed to make these missions possible. The success of Voyager 2 has shown that interstellar exploration is not just a dream, but a reality, and it has inspired a new generation of scientists and engineers to push the boundaries of what is possible. But the challenges of interstellar exploration are immense. The distances involved are vast, and the timescales are long. A mission to even the nearest star would take decades, if not centuries, to complete. And the harsh environment of interstellar space poses significant risks to any spacecraft that ventures there. But the potential rewards are equally immense. The discoveries that could be made by an interstellar probe are incalculable. They could reshape our understanding of the universe and our place in it. They could answer some of the most profound questions that humanity has ever asked. The legacy of Voyager 2 will also extend into the realm of philosophy and culture. The mission has forced us to confront our place in the universe and to consider the possibility of life beyond Earth. It has inspired artists, writers, and musicians to create works that explore the themes of exploration, discovery, and the unknown. And it has sparked a renewed interest in the search for extraterrestrial intelligence, as we wonder whether we are alone in the universe or whether there are other civilizations out there waiting to be discovered. In the end, the story of Voyager 2 is a story of the human spirit. It is a story of our desire to explore, to understand, and to connect with the cosmos. It is a story of our ability to overcome obstacles and to achieve the seemingly impossible. And it is a story that will continue to inspire us for generations to come. As Voyager 2 travels through the stars, it carries with it the dreams and aspirations of humanity. It is a symbol of our curiosity and our courage, a reminder that we are not alone in the universe and that there is always more to discover. So, as we celebrate the success of the Big Bang and look forward to the future of the Voyager mission, let us remember the lessons it has taught us. Let us remember the power of collaboration, the importance of innovation, and the value of perseverance. And let us continue to reach for the stars, knowing that even the smallest spacecraft can make the biggest discoveries. The journey of Voyager 2 is a reminder that the universe is full of wonders and that our quest for knowledge is never truly over. It is a journey that will continue to inspire us for generations to come. Thanks for watching. If you found this story as inspiring as I did, please share it with someone who needs to hear it. And don't forget to subscribe for more stories about the wonders of the universe and the incredible achievements of humanity. Until next time, keep looking up, keep dreaming, and keep exploring, because the universe is waiting, and it has so much more to show us.